Aromaticity is a word that makes you think of something that has a smell. And aromaticity doesn't mean that at all in chemistry. It actually has to do with the stability of a molecule. All of these molecules are aromatic. And the things that you see that are the same between them is they are rings and they have double bonds. So what we're going to do is talk about what makes these compounds aromatic. What makes them aromatic is the pi system. We already know that two carbons will form a pi bond by taking two p orbitals and overlapping them, and it makes a pi bonding and a pi antibonding orbital. Well, in an aromatic compound, all of the double bonds have carbons that have p orbitals in them, and all of them can interact together to make bonding orbitals and antibonding orbitals. And because of the way they interact, they drop in energy much more than just a regular pi bond, and pi antibond. The pi electrons in an aromatic system are reluctant to enter reactions that are common to other pi bonds just because they've been dropped lower. Now the antibonding orbitals are as a result pushed higher also. So the whole idea of aromaticity has to do with stability due to this really low energy level of electrons in the pi system. So what do we see in a pi system that's aromatic? We see conjugated double bonds. Conjugated means alternating double bonds with single bonds. What that does, it gives all these p orbitals are on each carbon in a row. So there isn't a carbon next to a carbon without each of them having a p orbital, if you can see what I mean. So every single one of these carbons, 1, 2, 3, 4, 5, 6, are all providing a p orbital to overlap in this pi system. So this is one pi system, not 3 different double bonds. This gives it, because it's one pi system, it has exceptional stability. You're going to see that we have different chemistry than an alkene. As the alkenes did addition reactions, what we actually will see is that the aromatic compounds do substitution reactions. So here's a picture of each of the carbons in the ring providing a p orbital to form the pi system. As you can see, there's no break in this. As you go from carbon to carbon, there's a p orbital from each one. Each p orbital has 1 electron in it. So there are 6 electrons in this system. We have 6 orbitals that are all at the same energy, and they're going to overlap. And when you overlap 2 orbitals, you get 2 resulting molecular orbitals, a bonding and an antibonding. When you overlap 6, you get 6 resulting molecular orbitals, 3 of which are bonding, 3 of which are antibonding. This is a picture of the molecular orbital diagram of benzene. There are 6 p orbitals, 1 with each an electron in each, that can overlap and form molecular orbitals. Of course, these p orbitals disappear because they're going to form the new molecular orbitals. What happens is you make 1, 2, 3 bonding orbitals and 1, 2, 3 molecular orbitals. The electrons always fall to the lowest possible place, so they all fall down into these 3 bonding orbitals. This is the energy of the p orbitals before bonding, so we call that the non-bonding energy. And you can see that the electrons drop a large distance and release a lot of energy when they go from being unbonded into a molecular orbital system. As a result, low energy electrons do not want to react. They're very low in energy. To make them react, they have to be pushed up. And it takes a lot of energy to push these up so that they could be reactive. And an example of the non-reactivity of an aromatic compound is the hydrogenation of benzene. It's hard to do. There are some catalysts that you can use. They require really high pressure, but even if we use the common catalysts of platinum and rhodium, palladium requires a bit more push than platinum and rhodium. But even platinum and rhodium, which are really active catalysts, they still require more pressure than a regular alkene, warmer temperature than a regular alkene, and a longer reaction time than the regular alkene. So there's a selectivity. Typically, we've been giving you hydrogenation of alkenes, and sometimes we even have benzene on the compounds, and we're showing they're not being hydrogenated. You have to work harder to hydrogenate that benzene ring, so you have a little bit of selectivity there. The heat of hydrogenation is an indication of how stable the compound is. So if you have a really stable compound that's low in energy, and when you do hydrogenation, it's an exothermic reaction, so it's dropping to a lower energy. If it's already low, when it drops to the lower energy on hydrogenation, not much energy is released. But if it's unstable, it's up at a higher energy, and there would be more release of energy. What we see is that a double bond releases about 120 kilojoules per mole. If I have 3 double bonds, I would have 3 times that. But benzene does not work as if it has 3 double bonds. What we get is about 150 kilojoules per mole from hydrogenation. So benzene has at least 150 kilojoules more stability than 3 separate double bonds. Benzene has characteristics that indicate that it's different from double bonds. If you were to have 3 double bonds and 3 single bonds in benzene, you'd expect 2 different length bonds. But what we find is they're all the same length, and that length is halfway between the length of single and double bonds. Not really halfway, it's closer to double bonds all the way around. But it's between those two lengths of single and double bonds. What we also find is the electron density is homogeneous around there. There's no heat of electrons in one place
typical
and dearth of electrons in another place.
If you mix it with bromine, you won't get it to add across any double bonds. You add acid, it's resistant to that. It doesn't do anything with acid.
There is no bending of
the reaction. There are reactions that will undergo, but they're limited and they require
all
special
of the bond
reagents,
angles are 120 degrees, which you would expect.
Cyclobutadiene and cyclooctatetraene are not aromatic. If you look at them, they look very much like benzene. They have double bonds that are conjugated and they're in a ring. And it just looks like they ought to be aromatic, but they're not aromatic like benzene. Why not? Well, let's take a look at the pi system and the electrons in it to try and figure out why they. Here are the molecular orbital diagrams for cyclobutadiene and cyclooctatetraene. Cyclobutadiene had 4 carbons in the ring, so 4 p orbitals. And what are they going to make? 4 molecular orbitals. One is going to be all bonding with no nodes, and one is going to be all anti-bondings out of sync with 4 nodes, or 2 nodes. And then, so we have the bonding on the bottom and the bonding at the top, which we always have, anti-bonding at the top, that we always have in our arrangement of orbitals when they're in a ring. That leaves 2 orbitals that are at the same energy, and they're going to be about halfway between the anti-bonding and the bonding. Well, if you look at that, the energy that's halfway between is going to be the same as the non-bonding energy. So cyclobutadiene has 4 electrons and 4 orbitals falling down into 4 molecular orbitals, but 2 of them go way down in energy, but 2 of them are going to be essentially like unbonded electrons at a very high energy. And notice they're not even paired. So this is a pretty high energy state. It's so high energy that it doesn't even like to form. It won't go planar. What it tries to do is be twisted so that it's not planar and what we call anti-aromatic. Anytime you have orbitals filled in such a way that the electrons in the ring, in the pi system ring, are like this in a non-bonding level and unpaired, they are what we call antibonding. And if I look at cyclooctatetraene, you would see the same thing. There's 8 p orbitals giving you 8 orbitals. Where are those orbitals? 1 fully bonding, 1 fully antibonding, and then you have pairs of orbitals going up the sides, basically, in regular spacings of energy. And if you look, that puts 2 orbitals right there at that non-bonding energy. All those 8 electrons fall down to the lowest possible place, but that's going to put 2 unpaired electrons at a non-bonding level. And again, very unstable. Now, we have this term here that says HOMO. What is a HOMO? A HOMO is a highest occupied molecular orbital. So if I look up here, my highest occupied molecular orbital is basically like free radicals. So they're going to be highly, highly reactive, very unstable, very hard to form. Same thing over here, free radicals. And we call this arrangement anti-aromatic. In aromatic compounds, what we find are all the pi electrons are in low energy pi bonding orbitals. All of the p orbitals contributing to the pi system are going to be in the same plane, so they overlap, and you are able to get this arrangement of orbitals that puts the pi electrons in bonding low energy orbitals. So you have this really, really, really stable electron situation. If you have something that's non-aromatic, you can have a conjugated pi system, but it has to either be non-planar or it's not going to be cyclic. Or sometimes you'll have a semi-conjugated pi system where it's conjugated in the ring, but it doesn't conjugate all the way around. For instance, in a 7-membered ring, if you have 6 double bonds, you would see that there'd be 1 carbon with 2 hydrogens on it that's not participating in that pi system. It cannot be aromatic. And then there's anti-aromatic. And in anti-aromatic, the HOMOs are non-bonding or even anti-bonding. And those electrons are very high in energy, and the molecule's highly reactive. If you form it, it reacts with whatever it can right away to get out of that high energy state. And it usually has a real high energy to form. So if you're removing maybe a hydrogen, a proton, in order to form it, that is a really very non-acidic proton or something along those lines. So we'll look at some of these. If you do form an anti-aromatic compound, what will often happen is the molecule will pucker to try and avoid being in a plane so that it is not anti-aromatic and it's just non-conjugated anymore because it's not planar. So how do you look to see if something is aromatic? To look to see if something is aromatic, what you do is you look at the number of electrons. You don't worry about the number of p orbitals, because what we find is the number of electrons actually is the key. The orbitals work out so that if you get the number of electrons figured out, from that number of electrons, you can say, oh, it's aromatic or anti-aromatic. Of course, now, to determine if something's non-aromatic, you don't look at number of electrons, you look at the arrangement of the molecule. Is it planar? Yes. Possibly it's aromatic or anti-aromatic. Is it conjugated all the way around the ring? Well, then it's possibly aromatic or anti-aromatic, etc. So all cyclic conjugated pi systems are going to have an orbital system which puts one pi orbital way down at the lowest energy. If it's an even number of p orbitals participating in the system, you're going to have one highest energy antibonding orbital, and then you're going to have pairs of degenerate pi orbital going up the sides or up in energy between the bonding and the anti-bonding. If you have an odd number of p orbitals, you just have one lowest energy phi and two highest energy antibonding. But I'm not going to get into a lot of detail with that with you. Really what you need to know is the molecular orbital diagram for benzene and understand it and be able to use it to explain things. Okay, this is showing you all the possible molecular orbitals for even numbers of p orbitals. And if you look, they're right over here on the left, that would be the orbitals that you have for cyclobutadiene. This would be for benzene. This is 8 for cyclooctatetraene, and this would be for a 10-membered ring. This would be for a 12-membered ring. This would be for a 14-membered ring. Wow, we have a lot of molecular orbitals here. Notice that for us to have only electrons, the highest electrons are bonding electrons below that this is the non-bonding level right here. And for you to have electrons only in bonding orbitals for these systems, you have to have 4n plus 2 electrons for them to be in bonding orbitals and be paired up. So here you would have 2, and that's what we find is cyclobutadiene, a cyclobutadiene system with only 2 electrons in it, would be aromatic. Here is benzene, and those 3 orbitals are filled with 6 electrons. If you have cyclooctatetraene, and there's only 6 electrons in the system, it would end up being aromatic. Same thing with, this would be pentaene, and it would have 10 electrons. In order to have aromatic electrons, you have to have this number of electrons, and the series 4n plus 2 gives you 2, 6, 10, 14, etc. And those pi systems with that number of electrons ends up being aromatic. And it extends on beyond just simple rings, which I'm going to show you how to look at it that way. So, for a conjugated planar pi system, if it's aromatic, it has 4n plus 2 electrons. So there's 3 things: conjugated, planar, and 4n plus 2. If it is conjugated, planar, and 4n electrons, then it's anti-aromatic. If you don't have conjugated, if you don't have planar, then what you have is a non-aromatic system.
go ahead and look at this structure and see if you can determine if it's non-aromatic, aromatic, or anti-aromatic. Okay, we have to count the electrons in the pi system. This is a fused ring, but all of these can participate in a 1 pi system, even though the ring is fused. So we count the electrons to see what type of rings, what number of electrons we have in the pi system. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then this carbon, it has only 1 hydrogen on it and these 2 single bonds, so these electrons can be in a p orbital. So if I continue to count, that would be 11, 12. 12 electrons is 4 times 3, so this is of the 4n number sequence. That means this is anti-aromatic. Repeat the same type of analysis on this compound and determine what its state is. Okay, so we go and count the number of p electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then because this has a positive charge, there's no electrons in a p orbital that are sticking up here. So the total number of electrons in this system is is 10. So that's 4n plus 2. That means that this compound is aromatic. So for benzene and cyclooctatetraene, what would you expect them to do? How would you expect them to react? Think about the aromaticity or lack of aromaticity and what you would expect aromatic compounds or non-aromatic compounds to do. Okay, so if I look at this, benzene, we already learned, undergoes substitution reactions and not addition reactions. Alkenes undergo addition reactions. Because cyclooctatetraene acts as an alkene and not as an aromatic compound, we would expect it to undergo addition reactions. Benzene, because it's aromatic, undergoes substitution reactions. We'll look at these reactions later on, and we will realize why there is a difference and go through the mechanism of these things, okay? But for now, just realize the aromatic compounds undergo substitution, non-aromatic undergo addition reactions. Which one of these would you expect to have the smallest heat of combustion? Well, if I look at them, I'm going to look for something that's aromatic because the smaller the heat of combustion, the more stable the compound had to have been. So if I look at this, there's some non-conjugation here, so this can't be aromatic. These are conjugated, but some non-conjugated there, so it can't be aromatic. This we know is anti-aromatic, so it would have a huge heat of combustion and release a lot of energy. This, however, has an aromatic ring, and so it would release very small amount of combustion. Notice these are all comparable to each other in that they have visually 4 double bonds, but the aromaticity of this compound makes it have the smallest heat of combustion. What is the name of the class of compounds to which this compound shown belongs? Well, this is an aromatic compound. You can see it looks like a bunch of benzene rings fused together. What do we call this? We call them polycyclic aromatic hydrocarbons.